We've already met Chad, so we're going to move on to the second half of our morning.
Yep.
Take it away.
All right. Make sure this. Yep. There's a light on it anyway. Okay. So the second part of this, right? I talked about the first part. I talked about the idea of quantum 1.0 technologies. They use these sort of quantum phenomena, particle nature of light, discrete states of atoms, wave nature of objects, to enable some technologies, specifically like lasers and transistors, that rely on quantum mechanics for their fundamental operation, but in practice serve as very classical sources of things. And I promised to talk about sort of quantum 2.0 sort of tools and techniques, which are going to basically be founded in using these 1.0 tools to exploit deeper quantum phenomena in a real way that depends on the quantum nature of those objects, depends on either the wave nature of material things or the particle nature of light waves. And this is a division that is not, it's not original to me. This is used by other people. And like most binary classifications, there's approximately as many definitions of the difference between quantum 2.0 and quantum 1.0 as there are people who use the term, right? And so, so this will be necessarily somewhat idiosyncratic. So this talk will be sort of an introduction to a particular classification of things that I'm calling quantum 2.0 technologies, and how they're used in measuring things. And I will admit up front that I have a definite bias toward atomic, molecular, and optical or quantum optics systems, because that's my background. I was trained as a cold atoms guy, so I come out of that world. I'm inclined toward those sorts of things. In talking about stuff here, a lot of the examples that I'll use are going to be biased towards searching for exotic physics, beyond the standard model kind of effects, because that's a thing that I personally find interesting, and also it's a topic that isn't otherwise covered here, right? The later speakers in the workshop are going to be talking about sensing, more concrete things, sensing magnetic fields from relatively ordinary phenomena, and for practical ends, I tend to give more examples from the other branch of the precision measurement world, which is looking for new physics in the 16th decimal place. And then I'll say up front that this is intended to be illustrative, not comprehensive. I give examples of a number of things in the talk. There's many more. There are plenty of people out there who will tell you that the experiment they did is better than the one I have a picture of, and this is an idiosyncratic personal version of this. I'm picking a few things that I think illustrate the point, but don't really only scratch the surface of the full richness of the field. So with that in mind, let me talk about, this is just going to be kind of a list of a series of technologies and areas of technologies that are, I think, things that count as quantum 2.0, and sort of a little bit of the history and uses of these things. The first thing I'll say is that the particle nature of light is one of the first things, is probably the first thing that's introduced that's a real quantum idea. And this is, originally Planck used this as sort of a mathematical trick to set up his derivation of the blackbody spectrum. Einstein really applied it, is the first to really apply it to light. Planck was applying this idea of connecting the frequency to the energy to the things that were emitting the light. But Einstein said, look, if we apply it to the light itself, we can understand the photoelectric effect. A photon comes along, it carries a discrete amount of energy, imparts that energy to an electron, right? If there's enough energy there, that electron will leave the material and carry the rest away as kinetic energy. Explains all the phenomena of the photoelectric effect. This idea of light quanta is somewhat reluctantly incorporated into Bohr's atomic model. Bohr wanted it to be classical wave, light to be a wave for a long time, but sort of eventually had to admit that that didn't work to explain everything and bought into the photon concept. And then Dirac, around 1930, quantizes the electromagnetic field and shows how all of this plays out. An interesting thing about this is, right, as early as the late 1930s, there are detectors that, at least in principle, are sensitive at a level that could detect single photons. And the tech for that is basically starts with Einstein and the photoelectric effect, right? You make a photomultiplier tube that consists of a metal surface. A photon comes along, hits it, knocks loose an electron. They use a high voltage to accelerate that electron into a metal plate, where it will knock loose several secondary electrons. Use another high voltage to accelerate all of them into another plate, where each of them knocks loose some number of secondary electrons, and so on and so on. You go through many stages of this, and at the end of it, you get a pulse that has enough electrons in it to make a click that you can detect as a single photon. Right, so one photon of light coming in principle, can get you a macroscopic electrical signal that you can record as, okay, that was a photon. The interesting thing about this is pretty much all of these experiments can be explained semi-classically. Right? The photoelectric effect is, if you teach modern physics to sophomores, right, what you tell them is the photoelectric effect, right, Einstein's theory, shows that light is particles, and therefore we need quantum mechanics. Actually, you can get essentially everything about the photoelectric effect from a model where the electrons have definite energy states, and the light is a classical wave, and that works actually perfectly well. And so there's a whole slew of experiments that get cited as, well, this shows that light is actually a particle, none of which actually show that light is a particle. The first experiment that actually definitively demonstrates that light cannot be not a particle is in 1977. It's Jeff Kimball and Len Mandel. And they did this experiment where they took a beam of sodium atoms, they excited some fraction of them to a higher energy state. Those atoms would decay, and there was they collected light from this beam, light emitted from those atoms. They collected and then sent to a beam splitter that sent it to two different detectors. And then what they looked at is how much time passed between getting a click at one of the single photon detectors and getting a click at the other. And what they see is this distribution of, there's a whole bunch of them at long times and very few at very short times. Right? There's no, it's anti-bunching. There's no, very little signal of, click on one, click on the other at the same time or close to the same time. And that shows that this light is behaving like a particle. Right, light is coming to the beam splitter, and the photon is detected either at one detector or the other, can't be detected at both. There's no way to have a classical wave model of light that gets you zero coincidences at these short times. The only way you can do that is if light is actually quantized and behaves like photons. So it's not, by 1977, before it's really fully nailed down that light has to be particles. So that is sort of somewhat of an aside, but confirms that we really need to grapple with light as a particle, and to be able to do experiments making use of the particle nature of light. So what are we going to do? If we're going to do that, we need single photon sources, and we need single photon detectors. And as I said, these photomultiplier tubes are available since the 1930s. The efficiency of those is relatively low, but they're incredibly robust. So that's been around. These days, they mostly use, most people doing single photon experiments use these avalanche photodiode detectors. that have, you know, efficiency of a few tens of percent through the visible range, which is, you know, good enough. You can see, put the graphic up here, like you can buy these from Thor Labs, which tells you that they're reliable, robust consumer products, because Thor Labs is nothing if not a consumer products company. They're not doing super experimental, you know, bleeding edge stuff, and that's a good thing for people who want to do these kinds of experiments. If you really, really care about the efficiency, there are now these superconducting transition edge detectors. It's basically a matrix of fine wires that you put just into the superconducting regime, and if one of them absorbs a photon, it kicks it up over the superconducting transition, becomes an ordinary metal again, and you see that as an electronic signal, and those are efficient up to like 90%. They work on these at NIST, and this is used to do really extremely low-level counting, where you really, really care that the efficiency is super high. But basically, you know, we have now technologies for ultra-low light levels that work down to the single photon level for all kinds of things. If you want to do an experiment where the light level coming back is going to be, you know, single photons coming in one at a time, you can do that pretty readily, and that's a really nice technology to have. You also need a way, if you want to do experiments that use single photons, you need a way to know that you have one and only one photon. There's two main technologies that have been used for this. The earliest was basically just using atoms, exciting an atom to a very high-lying energy state, one that will decay back to the ground state via the emission of two photons. This is, I believe, calcium, that you excite it up, and then it will decay back to the ground state by first emitting a 550 nanometer photon, and then a few nanoseconds later emitting a 423 nanometer photon. So you get one, and then you get the other a very short time later, smaller than the counting delay in your electronics. So you can use one of these as a trigger for the other, right? You say, if I see a 550 nanometer photon here, right, I know I should be expecting there to be a 423 nanometer photon over here at, you know, within 10 nanoseconds of that. And so it gives you a good way of getting a source where, you know, you see one, you know to look for the other. You can gate your detector on and look for coincidences between these things. Problem with this is there are atoms, they emit spontaneously, they go into 4 pi, so it could go in any direction. The chances of emitting in the precise direction of your detectors is quite low. So the count rates from these tend to be very low. Good for demonstration experiments, not good if you want to do something that, you know, takes finite time. For a lot of things you'd be interested in doing, the experiment, you know, data acquisition time is longer than the mean grad student lifetime. So the real game changer of a source is this parametric down conversion sources. So you get a nonlinear crystal that you shine in, basically an ultraviolet photon, and get out 2 infrared photons. And the nice thing about this is, you know, you use a laser as the input. The 2 beams that come out, the frequencies of the 2 have to add up to, because of conservation of energy, the frequencies of the 2 photons that come out have to add up to the frequency of the one photon that came in. And then these materials tend to have a different index of refraction for the infrared than the ultraviolet, which means that to conserve momentum, they have to come out at an angle. And you know the angle between the 2 photons that come out. So if one comes out in this direction, you know that the other one is coming out, you know, within a very short window of time, and, you know, at an angle of 6 degrees away from the first one. So you know not only when to look for the second photon, but exactly where to look for it. And so this gets you relatively well-defined beams and high fluxes of photons, enough to do all kinds of really interesting stuff. So So these are sort of the workhorse sources for people who do single photon experiments, and there's a wide range of single photon things that people do. The other thing that these can do is these can be polarization entangled. The rules governing how these photons get emitted in the cascade sources, or how they're emitted in the down conversion sources, to conserve angular momentum, there's a relationship between the polarizations of the photons. If one is polarized one way, you know that the other must be polarized in a particular way as well. And that's the definition of an entangled state. That's a state where the polarizations are indeterminate. Could be this way, could be that way. But if this one is vertical, then this one in the other place will also be vertical, and you know that for certain. Which is a source of polarization entanglement. And that's sort of the second area of quantum 2.0 technology, is exploiting this notion of entanglement of photons. So I can get a source that produces pairs of photons, right? I detect one over here with a particular polarization. I know that there's going to be another one over here with a particular polarization that's correlated with the first one. And you can exploit both the fact that there is, just the fact that there is a photon physically present there, to know that you're sending one photon into some experimental apparatus. You can also exploit the fact that those polarizations are correlated to do various entangling things. This modern notion of entanglement comes out of the Einstein, Podolsky, and Rosen paper, 1935. Really, Einstein, Podolsky, and Rosen basically, like I said in the first part, kicks off basically 3 decades of people yelling at each other about philosophy, but really only yelling at each other about philosophy, not actually doing anything about it. It's not until the 1960s that John Stuart Bell looks really closely at this problem and says, okay, let's think about what are the consequences of this being non-local, right, of this correlation persisting across very large distances, larger than you could send a message from one place to the other. And let's think about what does that say about the nature of reality and what kinds of experiments we could hope to do. And so the mid-60s, Bell proves a theorem that it's possible to, by doing the right kinds of observations, distinguish between a theory that's truly non-local, where these correlations don't respect the speed of light limit, separating the measurements, and one where the values of the possible measurement outcomes are determined in advance. Which is what Einstein, Podolsky, and Rosen are pushing for, is there should be a way to say, all right, when the photons leave the source, this one says, if they try to measure me vertical versus horizontal, I'm going to come out vertical, and this, and this one says, okay, then I'll do the same right over here, where they've agreed in advance what the outcomes will be. That gets different experimental results than a theory where those states are truly indeterminate until they're measured. And you can go and test that. And these both kinds of photon pair sources produce atoms that have that entanglement. And this gets tested in the 70s and 80s. John Clauser is the first one. He does this with a cascade source in the early 1970s. And then Elena Spey does a series of experiments in 1980-81, where it's a series of 3 experiments where he shows that the outcomes of the measurements, violate Bell's inequality, are only consistent with the non-local version of quantum mechanics, and he also closes a bunch of loopholes. Right? There's things there's arguments you can make to say, well, actually it could be a local hidden variable theory, but there's some quirk of your apparatus that leaves room for us to sneak that through. He closes a couple of those. And then Anton Zeilinger, through the 90s, does a whole career's worth of experiments mostly using these down conversion sources, and does, if you're clever about the way you organize it and you have access to these 90% efficient detectors and so on, you can do loophole-free tests of the Bell theorem and show that there's really no exotic theory you could construct where these photons are leaving the source with a predetermined list of measurement outcomes. There's those, formal photos are from when they won the Nobel Prize for this work in 2022. So entanglement's a very real thing, demonstrated in countless experiments now, and is now a resource that you can exploit, right? You can do experiments where you use these entangled photons to connect things in a quantum way, to you can take an atom that's in some superposition of states, tie that superposition into a particular state of a photon, of a pair of photons, send those photons to other atoms in other places, and reproduce the state of that atom in an atom in a distant location. And so this is incredibly useful for transmitting quantum information across networks, across long distances. So I said in the first part, there's this much richer dynamics than simply state 0, state 1 in these quantum systems, this whole range of superpositions and populations and phases. You can map those things from an atom in one place to an atom in another place by using these entangled photons to do it, using this notion of entanglement. This is a figure from a paper that used 2 trapped ions in separate vacuum chambers, and it could induce those atoms to emit photons, entangle the photons, and then make entangled states of the ions, even though they're not in the they're not that far apart, but they're in different physical enclosures, right? One's in a vacuum chamber here, the other's in a vacuum chamber there. So this is really cool stuff that you can do in the quantum information networking space. You can also do things that are more straightforwardly measurement-like. You can do things like ghost imaging, where you by looking at correlations between these photons, you can make an image of something without that thing ever absorbing the light. You look at looking at the distribution of a photon, spatial distribution of a photon that's entangled with the one that interacts with the object. You can map out a picture of an object without directly interacting with that object, and that's kind of a cute variation of this. There's also all kinds of things you can do with quantum cryptography is a big area of these things, using these to generate, to encode messages that you send between places to essentially generate a new one-time pad every time you want to send a message back and forth that you can prove can't be intercepted by somebody else. So it's a big area in information and communications. Third thing that is, I'm putting in quantum 2.0 because it really, sort of requires lasers and a fuller understanding of quantum states to make it work. And I'll call this, right, internal state control. And the idea is, in one of the slides in the last talk, I showed this internal state structure of sodium, and you see 2 lines with 0 magnetic field, and if you turn on a magnetic field, it splits into like 4 or 6 lines. It's this multiplicity of states. That comes about because these atoms have internal states that are very complicated, and there's many states that have the same energy, but different values of the angular momentum. Either the angular momentum of the atom, of the electron orbiting the nucleus, or angular momentum associated with the electron's spin. So the electron behaves, the electron is, I am contractually obligated to say, the electron is not literally a spinning ball of charge. That doesn't work. But it behaves as if it were a spinning ball of charge, has a small magnetic moment that can be pointing up or pointing down. It can be in one of 2 orientations. And that contributes to this internal state dynamics. So these atoms have this complicated array of internal states, and if you just grab you go to Costco and grab a sample of sodium atoms, right, you're going to get a bunch of them in all kinds of different states, sort of randomly distributed. But lasers give us the ability to refine that and put everything into one state. And the way this works is the rules for absorbing and emitting light depends on the polarization of the light and these internal levels. So these levels get indexed by a quantum number that refers to the electron's angular momentum. And if I start in a particular state, say the minus 1/2 state in the lower energy state here, right? If that absorbs light with a right-hand circular polarization, it will increase that quantum number. It'll go to the +1/2 in the upper state. If it was illuminated with left-hand circular, it would go to the -3/2 state. If it is illuminated with linear polarization, it would just go straight up to the -1/2 state. So which direction, where the atom moves to depends on the polarization of the light. And this allows you to do a process that's called optical pumping to prepare the system in a particular state. So, right, I excite this, say I put on right-hand circular polarization, I go to the +1/2 state. The atom in the +1/2 state in the upper state can decay back to the lower energy state by one of two ways. It can emit a right-hand circular polarized photon and go back to where it started. But if it does that, it goes back to where it started, and then the next laser photon that comes along is also going to put it in the +1/2 state, where it can either go back to where it started, or it can emit a linearly polarized photon, drop down to the +1/2 state. And then when it's in the +1/2 state, the only place it can go is to the +3/2. Here, it can only go one to the right. And then once it's there, it can only come back to here. There's no +3/2 in the ground state that it can decay to. So this is a process that inevitably puts all of the atoms into this state. Right? I start with a bunch of atoms randomly distributed between -1/2 and +1/2. The +1/2 ones just go back and forth between +1/2 and +3/2. The -1/2 go up to +1/2 and sometimes back to -1/2, but sometimes to +1/2. If they come down to +1/2, then they're stuck there. They just go back and forth between the same two internal states. If they go back to where they started, the process starts over and continues until they end up here, where they're just going back and forth between these two states. So this is referred to as optical pumping because it has the effect of, and you can start with many more. This is the simplest illustration with just +1/2 and -1/2 in the ground state. There are ground states that are like +13 if you get the right kind of atoms. You can start it all the way at one end and inevitably end up all the way at the other end in one particular quantum state. Just by using the application of laser light with appropriate polarization. So this gives us really fine-grained control of the internal state of these atoms. If you've got these atoms hanging around, you can put all of them in any state that you like. And that's a really powerful thing to be able to do. What kinds of things can you do with this? Well, you can use this for quantum sensing of things. Those angular momentum states are associated with the magnetic properties of the atoms. Right? If you put all of them in the state of maximum angular momentum, that essentially acts like a magnetic, little magnetic moment. So I can take these atoms, pump all of them into the extreme internal magnetic state. That gives a magnetic moment to that gas of atoms. And then that will interact with other magnetic fields, right? That can also interact with if you have atoms that have just nuclear magnetic moments. You can polarize the nuclei by interactions with the atoms that you've optically pumped. So you can say, take a sample of helium gas, interact it with these atoms that are being optically pumped. The collisions between the helium and the other atoms will put all of the helium nuclear spins pointing in the same direction. And then you can use that, for example, to do polarized magnetic resonance imaging, which is a cool thing that people have done with this. You can also use this as, the fact that this is a magnetic moment, you put it in a magnetic field, that magnetic moment will precess in response to an external field. And so, if it's pointing this way and you have an external field that's pointing, perpendicular to it, it'll move in the plane, it'll rotate. And you can read out that rotation of the magnetic field by shining a weak probe beam through and looking at the effect that has on the polarization of the light through the Faraday effect. If you're interacting polarized light with a magnetized material, you can rotate the polarization of the light in a way that allows you to read out what is the magnetization of the material and detect really small fields. This picture here is from an experiment done in the Romalis lab at Princeton, where they set up a magnetometer. They have potassium atoms that they optically pump, helium gas that might be krypton gas. I'm forgetting which version of this it is, but it's a noble gas whose nuclei get polarized by collisions with the atoms that they're optically pumping. And then they create this magnetization in the nuclei and magnetization in the atoms. And the nuclear magnetization tends to cancel out external fields, makes them sensitive to rotation of the system and also forces that look like rotation of the system. So they're looking for forces that depend on the orientation of their apparatus. They see a clear signal here. You see this sinusoidal thing is, they're measuring effectively what their magnetic field is. It's in femtotesla, if you want to know like how small a magnetic field they're talking about. You see there's a big difference between, there's these big peaks when their apparatus is pointing north or south compared to when it's pointing east or west. That's because they're doing this in Princeton, New Jersey, which is at a latitude of 40 mumble degrees. And so one of Romalis's grad students in his thesis defense pointed out, sort of said flippantly, like, well, if we did this experiment at the South Pole, like that systematic effect would go away and we'd be much more sensitive to more exotic things. So they did the experiment at the South Pole. So that's Romalis at the geographic South Pole. They have a version of this apparatus now set up at the Amundsen South Pole Station. The grad student who made the original flippant suggestion says he was very happy that he waited until his thesis defense to make that remark so that he wasn't the guy who had to go spend months in Antarctica getting this experiment working. This is sort of one of the core techniques for making sensors, quantum sensors of magnetic fields, right? You can optically pump atoms into these extreme magnetic sublevels and then use those behave as little magnetic moments that are very sensitive to the presence of external fields and is a powerful technique for picking those up. The other thing you can do with these internal state control is to do more with this block sphere picture. So I mentioned that we want to think about these states of quantum systems, right? We have to think of not just 0 or 1, but some admixture of 0 and 1 with some phase between them, right? States on the surface of a sphere. And right, having precise control of laser type sources, you can choose the frequency of your light, you can choose the intensity of the light, you can choose how long the light is interacting. And that combination of detuning, intensity, and duration will determine what's going to happen in some combination of different changes in populations and changes in phase. And this can be understood as doing rotations on this block sphere. So if you apply one kind of light pulse, you can do a rotation about, say, the x-axis in this block sphere picture, and take a state that starts at the South Pole and rotate it up to any angle you like, changing the admixture of how much 0 and how much 1 you have in your state. You can also do a z rotation, a rotation about the z-axis, which is just changing the phase between 0 and 1. Right? So you do something that if you start off on the equator with your state vector, you apply a z rotation, you just go around east to west. Right? You increase that azimuthal angle. This also, the way this is set up, this tends to happen during free evolution. So if you you prepare a state, you just sit around and wait for a while. These block state vectors tend to clock around the equator of the state. They rotate about the z-axis, accumulating phase at some rate. And so we can understand free evolution in that same kind of way. There's two particular kinds of rotations that people will reference. One is a pi over 2 pulse, which is, these are both x rotations, but you rotate about the x-axis by an angle of pi over 2, 90 degrees. So that is, you start out at the South Pole, you come up to the equator, and that's a pi over 2 pulse. That's a thing that you frequently want to do. That consists of going from, say, purely 0 or purely 1 to an equal admixture of 0 and 1. Right? So 50% chance of finding it in state 0, 50% chance of finding it in state 1. This is exactly your Schrodinger cat kind of superposition state. The other kind of pulse is a pi pulse, which does an x rotation by an angle of pi, right, or 180 degrees. So if you start out at the South Pole, you end up at the North Pole. If you start out at the North Pole, you end up at the South Pole. And this is another rotation you can do by precisely controlling the frequency and intensity and duration of your laser interaction. You can specify, I'm doing an operation that's going to rotate this state vector by 90 or 180 degrees around the x-axis of the Bloch sphere. This combination of things allows you to take these subtle differences in phase that accumulate from different interactions and turn them into differences in population. So, for example, if I'm starting on the equator and I do a pi over 2 pulse, right? If I'm starting on the plus y-axis, I do a pi over 2 pulse on the x-axis, I end up at the North Pole. Right, and that's my population is now 100%, whichever state I called the North Pole, because there's depending on whether the textbook I copied this from. So this was done by computer scientists because they make the top 0 and the bottom 1, and physicists tend to put 0 at the bottom and 1 at the top. But I copied the original figure from a book done by computer scientists. Right. If you've got a different phase, if you're starting a different phase, you start out not on the plus y-axis, but you start out some distance off that, right? When you do a rotation of 90 degrees, you don't end up at the North Pole. You end up, right, at the latitude of Princeton, New Jersey, right? You end up, kind of 45 degrees north. Because you're doing a rotation about the x-axis starting at a point that isn't right on the y-axis. Right? If you're starting somewhere else, you describe a smaller circle off to the side of this, and so you get a different population in the top, in the upper of the states. Right? So you can use this to map a difference in phase onto a difference in population. And a difference in population is a thing you can read out. Right? I can do projective measurements and I can say, okay, I want to know how many of, I've got a bunch of atoms. Are you in state 0 or state 1? Right? And you do that measurement, you can determine what was the probability of being in state 0, what was the probability of being in state 1 after some sequence of operations. That's a projective measurement that you can easily do. And you can, anything that you can turn into a phase difference, you can now turn into a population difference by doing these Bloch sphere rotations using the control that's afforded by having laser sources as a way to do this. And this shows up in a whole host of the quantum sensing measurements that people do. You can think of the measurement process as a series of these Bloch sphere rotations. So, any kind of interaction that shifts the energy levels of atoms or molecules around, this is a figure illustrating schematically a search for a electric dipole moment of the electron. You put atoms in a combination of a magnetic field and an electric field that point in the same direction. The magnetic field will shift the energy levels by some amount that's well understood. If the electron has an electric dipole moment, it'll get, in one orientation, they'll shift a little bit more. You reverse the orientation of the electric field compared to the magnetic field, they'll shift in the opposite direction. And that shift shows up as, these are molecules that start off with the same phase. They get out of phase with each other by different amounts depending on the relative orientation of these. You can read out that phase difference as differences in population. So this is anything that makes a tiny difference in the energy levels turns very readily into a phase difference. If you have this kind of fine-grained control of internal states, you turn that phase difference into a population difference, and that's easy to detect. So, well-controlled qubits prepared in any arbitrary state. Once you've got them, you can map these small shifts, perturbations, into changes in populations that are easy to pick up. So this is a key component of doing these things. Fourth thing I would say is interference, right? Using the fact that these things are wave-like and interfere with each other to do measurements. Right, when I was talking about pre-quantum precision measurement, I said essentially everything that you do with light waves comes down to the fact that they interfere with each other and you get these interferometric signals. We can do that with these internal states using these block sphere vectors by sort of splitting an interaction in two. This is a method that's developed by Norman Ramsey in the late 1940s. Of doing ultra-high precision spectroscopy, and it's core to every atomic clock that was ever built, essentially. Is you have a microwave source, you're going to interact with a set of atoms. Instead of just putting that microwave source on for an arbitrary length of time and seeing what's the probability of the atoms ending up in the changing states, what you do is you arrange it so that they interact with the microwaves for a short time, then they evolve freely for a long time, then they interact for another short time, and after that you look at the state. And you can understand this in terms of these block sphere vectors, right? That first interaction is designed to do a pi/2 pulse. So I take my atoms start off at the South Pole, I rotate them up to the equator. Then during the free evolution, those atoms are going to clock around, right, around the equator. They're going to accumulate phase as they go around the equator of the sphere. And then the second pi/2 pulse is going to be another rotation about the x-axis of the block sphere that changes your phase difference into a population difference. So if your phase accumulation has brought you back to the y-axis, when you do that second rotation, you come all the way up to the North Pole, and then all of your atoms are in the other state than they started in. If, on the other hand, you're 180 degrees off, right, that rotation about the z-axis takes you from the minus y-axis down to the South Pole, and you end up back in the state you started in. The amount of phase you accumulate depends on how long the atoms are allowed to freely evolve, and gets you this signal that oscillates rapidly in a way that depends on that time. So then you do this projective measurement to determine how many atoms are in state 0, how many are in state 1. The signals look kind of like this. If you scan the microwave frequency over a wide range, you see this overall envelope that's kind of, This is the full range of things that the cesium atoms would absorb. And then it's modulated by this very fast oscillation. If you zoom in, you see these fringes that go from 0 all the way up to 1, very high contrast. The 0 points, the center, this is the difference from the cesium transition frequency. If the frequency is exactly perfect, then you get a 100% conversion to the other state. If you're off by 1 hertz either direction, you get 0. Right? Everything comes back. If you're off by 2 hertz, you're 100% conversion again, and so on. The difference here, the line width of those fringes is inversely proportional to the free interaction time. So this says these are atoms that were freely evolving for approximately 1 second. This is from a state-of-the-art atomic clock, a cesium fountain clock at the U.S. Naval Observatory. So yeah, this is what the atomic clock guys do to measure, right? So they can measure by tuning their microwave source and looking at what comes out of these Ramsey fringes. They can get their frequency in a single shot to within about 1 hertz out of 9,192,631,770 hertz. That is the definition of 1 second in the SI. So incredibly sensitive technique for looking at frequencies of things and looking at converting these phase differences into population differences, and thereby using projective measurements to read these things out. So this, breaking this excitation into 2 stages gets you a lot of sensitivity to relative phase, and this is virtually any phase-sensitive measurement that you look at has an aspect of this in it, right? So this is, as I said, this is a schematic of how an experiment to look for an electric dipole moment of the electron works, right? This is data from a recent experiment doing, looking for an electric dipole moment of the electron. And what you see here is, the axis down here is labeled Ramsey time, right? They're looking at the relative populations of 2 states in a molecule. I believe it's hafnium fluoride ions. I don't think they have the name in that. But it's these crazy, unpleasant molecules that you have to do these things in. You can see that there's these changing populations of these different states that they track, and the frequency at which those things vary depends on the interaction time. And the exactly how much population you have in those states depends on is there an interaction that's shifting the phase of these things in a small way. The answer is no. Their result is consistent with 0, improves on the previous upper bound by a factor of about 2.4. And this is testing exotic theories of physics. It's looking for particles with masses up to 10 to the 13 electron volts, which is more than you can get in any sort of plausible accelerator now. So it's a really sensitive test of beyond the standard model physics. So there's a whole community of AMO people, quantum optics people, that do this kind of thing. And it's leveraging this power of this Ramsey interferometric method to do these really precise measurements. Okay. 5th quantum 2.0 for measurement thing I'll mention is the notion of quantum degenerate gases. And this starts with the notion of Bose-Einstein condensation. This was predicted in around 1925. It's work on quantum statistics by the Indian physicist Satyendra Nath Bose, who worked this out is developing lectures on quantum statistics, worked out this interesting effect, sent it to journals in Europe who said, you're some guy in India. We don't know you. We're not going to publish this. Then he sent it to Einstein personally, who read it and said, this guy's onto something. Wrote up a short paper building on Bose's work and sent both of them to the Zeitschrift for Physics and said, publish this. And I said, oh, well, it's Einstein, so they published it right away. And the key idea here is that a way to understand what's going on is that you have these particles that are going to behave like waves, and they also have these statistical restrictions. So if the particles have integer spin, they're the class of particles called bosons after Bose. Those particles are perfectly allowed to occupy the same state. You compile as many of them into the same, they can all have the same collection of quantum numbers, same momentum, energy, spin, right? All of the things can be exactly the same. That's a thing that can happen. They don't know that that's a thing that can happen because at high temperatures they bounce off each other like little billiard balls, because the wavelengths associated with atoms moving at room temperature velocities are so small that the interaction basically lasts no time at all. You start to lower the temperature, you make those atoms move slower and slower, they start to behave more and more like fuzzy balls of waves. When they interact with each other, there's a longer period in which they're in contact and they're aware of the presence of other atoms. At some point, those wavelengths become long enough that they start to be comparable to the spacing between atoms in your gas, at which point every atom is suddenly aware that there are all these other atoms, and hey, we could all lower our energy by going to the lowest energy state available. We could all jump into that state, and that's what happens. There's a place where all of these particles condense into a single wave function when you cross below some critical temperature. The wavelengths overlap, they become aware of each other, to anthropomorphize a bit. They become aware of each other, and then they all occupy this single lowest wave function. This is predicted in 1925. It's related to the physics behind superconductivity and superfluidity, but those systems are in liquids and very strongly interacting. You can actually do this in a gas where the particles don't interact strongly with one another and in very dilute atomic vapors. And this is first done in 1995 in rubidium at Gila out in Boulder, and then very shortly thereafter in sodium atoms at MIT, in the group of, it's Eric Cornell and Carl Wyman at Gila, Wolfgang Ketterle at MIT. And then quickly, lots of other elements, lots of other isotopes in subsequent years. This is important because it's essentially, millions of atoms occupying a single wave function all at the same time. And it's kind of an ideal source for lots of kinds of experiments. So bosons is one category of particles. They do this. They undergo this Bose condensation. The other category of particles are called fermions, after work done by Enrico Fermi, who, as he tended to do, was sort of fleshing out an idea that had been thrown out by Wolfgang Pauli. It's the notion of Pauli exclusion, that you have two electrons are forbidden from having the exact same set of quantum numbers, right? You add up the energy, the angular momentum, the spin of the electron. You can only have one electron with a particular combination of those. If you want to add a second electron, it needs to have one of those numbers be different than the others. Pauli threw this out as a way to explain the structure of the periodic table. Fermi worked on the statistics of this. Dirac simultaneously, he wasn't aware of Fermi's work, but he was, came up with this independently shortly after Fermi. And the key idea is, is just this Pauli exclusion, that you cannot have two electrons in the same atom with the same collection of quantum numbers. This explains everything about chemistry, right? If you took chemistry in high school or college, right, you spend a lot of time drawing these up and down arrows for different orbitals and loading electrons in, say like, which column of the periodic table does an element with 17 electrons land in? You do it by drawing these up and down arrows. That's Pauli exclusion. That's this Fermi-Dirac statistics. If you're looking at enormously huge number of electrons inside a solid, the same thing happens, but it fills up an energy band. And this is what determines the difference between an insulator and a conductor, right? An insulator is a state where all of the available energy states right up to the edge of a band gap are full. And so to move an electron to make a current flow, you would need to put in a lot of energy into that one electron to get it to a place where you can give it a different kinetic energy and make it flow through the material. Whereas a conductor is one where the states fill up and then there's empty states in the same band above it, so you can increase the energy by a tiny amount and cause the electron to move through the system. If you're not at zero temperature, there's also some thermal excitation. And this is the Fermi-Dirac distribution, which is the most famous quantum formula ever to appear in an episode of Pinky and the Brain. Seriously, there's an episode of Pinky and the Brain where this is cited, which tells you that at finite temperature, all of the states up to some point are basically filled, but a few of the right below the Fermi energy are unpopulated, and those electrons are moved up to higher energy states. This is what puts the semi in semiconductors. Semiconductor is basically just an insulator with a really small band gap, such that at room temperature, a few electrons pick up enough energy from this distribution to give them, to put them up in the higher band where they can conduct current. So a semiconductor conducts, the only reason a semiconductor conducts at all is this Fermi-Dirac distribution that says some of these are excited. So this is the other category of particles in the world. You have bosons that happily go into the same state. Fermions do not. This shows up in condensed matter physics. This also shows up in ultra-cold atoms. Same way you take a gas of bosons and cool them down, they become aware of each other, they all condense. You take a gas of fermions and cool them down, they become aware of each other, and they all say, like social distancing, right? And they go into different states, they're not allowed to be together. These are images of a cloud of trapped atoms, lithium atoms of two different isotopes from the lab of Randy Hewlett at Rice University. If they do this with a bosonic isotope, right, you can think about this as the distribution of atoms among energy states in the trapped potential that's holding them. And initially at high temperatures, they're scattered all over the place. As the temperature cools down, sometimes you get two of them in one state, but not all that often. And then there's a transition temperature at which suddenly a large fraction of them go into the lowest state, and you have maybe a couple extras. This shows up as your cloud of atoms is big. It gets smaller. It gets as it gets colder, and then at some point it suddenly gets really, really tiny, right? As they all jump down to the very narrow state. You do this instead with the fermionic isotope. As you cool it down, you start with atoms distributed over a wide range of states. The range of states they're distributed over decreases, but you fill up these available states, and you fill up to some level, and then you can't squeeze it any tighter, right? These states are distributed over some region of the trap potential. Right, you end up with an atom that's in a fairly wide state and can't go any lower because all of the states below it are occupied. So you see a cloud of atoms that as you lower the temperature gets smaller, and then stops getting smaller because of this Pauli exclusion. This becomes a degenerate Fermi gas. This was first done at Gila, again in 1999 in the lab of the late, great Deborah Jin. And then, again, very quickly followed up by various other groups. And Hewlett was working with lithium that happens to have both a fermionic and a bosonic isotope, so it could do this really nice direct comparison of the two. What are these good for? You take a bunch of fermions, you put them together. That's like what electrons are doing inside of solids, right? And you can put this together with the quantum technology of using light to exert forces on atoms and make an optical lattice that is a periodic structure of locations at which the atoms would like to be trapped, right? And then you stick a bunch of fermionic atoms in there. It's going to look exactly like a system of electrons inside a crystal lattice of a solid. Only the role of the electrons is being played by atoms which are big and slow and heavy. So processes that take picoseconds, right, take milliseconds instead. So then you can look at real-time dynamics of these analogs of electrons moving around inside this potential, and how do they distribute themselves? If you perturb the distribution, what happens to it after that? If you turn on interactions between the atoms such that they can pair up and form bosons, right? That's analogous to the Cooper pairing that happens in a superconductor. You can see the formations of superfluids and look at these phase transitions in an atom by atom kind of way. And these optical lattices are inherently structures that have, your trapping sites are kind of a wavelength of light apart, give or take, which means you can image them, right? You can do, if you get high quality optics, you can look at the distribution of atoms and see atom by atom, site by site, what's going on. And so look at these. So this is a figure. The grid at the top is the grid of positions in an optical lattice. The color tells you whether it's occupied with an atom or not for various conditions. And it gets you these, you can see phase transitions happening as you change the interactions between the atoms and that sort of thing in a site-resolved atom by atom manner, which is amazing. And there's all kinds of really cool precision condensed matter things you can do with these kind of degenerate Fermi systems. BEC type systems are used primarily as, the phrase sort of was in vogue for a while in the late 90s and sort of fell out, but is not inaccurate in that you can think of these as kind of an atomic analog of a laser, right? I have a bunch of atoms that are all in a single quantum state. They're all in phase with one another. They're all moving. They have the same momentum. You can treat that as analogous to a laser and think about doing things with atom waves that you would do with light waves. Which sets up the next item on the list here, which is the notion of atom interferometry. So I said, one of the core quantum phenomena is this notion that material objects have wave nature. They have a wavelength that's equal to Planck's constant divided by the momentum. And this is demonstrated even with really big things. I love this figure. This is an interference that comes about from sending a buckyball molecules, carbon 60 carbon atoms bound together in a soccer ball type structure, sending that through a silicon nitride diffraction grating. So they machined slits in a silicon nitride wafer, sent a beam of buckyballs through it, and looked on the far side, and what you see is unmistakably interference fringes, right? So these molecules that have 60 carbon atoms in them are behaving like waves, right? Big, complicated, heavy molecules showing their wave nature that works. This is initially in Zeilinger's lab. I mentioned him last time. It is, one of the other authors on this, Marcus Arndt, has carved out a really nice career of just doing this with progressively more ridiculous organic molecules. So these molecules with hundreds of atoms in them through carefully constructed grating type structures and showing that they interfere like waves. And he's working his stated goal for years has been to do something that's plausibly alive, right? To do like a virus or a bacterium, get to the point where they can do these experiments with something that's that big and complicated. From the standpoint of precision measurement, this is really interesting because, right, the bigger you make the mass, the shorter you make the wavelength. Right, and the smaller the wavelength, the more sensitive you can be if you're doing interferometry experiments. So if you're looking at like a Michelson interferometer, right, where an extra wavelength, quarter of a wavelength worth of path lengths changes you from constructive to destructive interference, right, these wavelengths are really, really small, right. On top of that, these atoms pick up phase shifts that affect their interference due to, well, they have mass, so they're affected by gravity, right? So they can pick up phase shifts due to gravity. They have this internal magnetic structure, right, that's affected by magnetic fields, right? You can see the influence of magnetic fields by doing this. And they're potentially sensitive to all manner of other forces that you can detect by doing interference experiments, the same way you do interference experiments with light. Only the range of things that affect the phase of light is much, much narrower than the range of things that affects the phase of atoms. So some examples of this. This is pictures from an experiment at Stanford by Mark Kasovich, who, full disclosure, I was a postdoc with him when he was at Yale, so I'm somewhat obliged to include references to his work. But also this experiment is completely insane because this is, they get samples of rubidium atoms, they cool them to nanokelvin temperatures, and then they launch them up through a vacuum system that is 10 meters high. Right, so they take these clouds of atoms and toss them upwards. He inherited a lab from the people who were building Gravity Probe B that had a 15-meter high, deep pit in one corner, and he said, "What can we put in that?" And made this atom interferometry apparatus that is 10 meters high. So they do a test of the equivalence principle is this. So they get one rubidium has two isotopes. One of them has a mass of 85 atomic units. The other is 87. They cool both of them simultaneously to nanokelvin temperatures, launch both groups of atoms up into this structure, so they're flying upwards. And then they apply some laser pulses that split those atoms apart by giving some of them a extra momentum kick. They separate in the interferometer. You do another laser pulse that reverses the momentum kick, bring them back together, and then recombine them. They interfere with each other in a way and give you outputs in the state with zero net change in momentum and plus or minus 2 photon momenta change in momentum. And you see these interference fringes. And from those interference fringes, you can deduce how much phase evolution happened while these things were flying up and down under the influence of gravity. These are both affected by gravity throughout this process. They're accelerated, down toward the Earth at 9.8-ish meters per second. If there's a difference, right, if being heavier leads to a different acceleration, that would show up as a change in the phase of this, which would shift your interference pattern and show up. Their measurement is consistent with 0, but at the 10 to the minus 12 level. So the acceleration of gravity for rubidium-87 and the acceleration of gravity for rubidium-85 are identical to the 13th decimal place, right? That these things are the equivalence principle works. Einstein was right. That's in the first sentence of every news story about these particles, because if Einstein ever said anything about a subject, he has to get mentioned in that. I just think this is an extreme example of atom interferometry. At the top of the highest point, the two wave packets are separated by something like 10 centimeters. Right, so these atoms are split. It's rubidium-85 atoms that are a superposition of this state and this, of being here and being here at the top of their vacuum system. And you could pass your hand between them if you were inside the vacuum chamber somehow. So really cool. You can also use this to look at gravitational effects in other systems, and also measurements of the fine structure constant. You can do a clever thing called a Ramsey-Bourdet interferometer, where you, in addition to doing this momentum transfer to split the atoms apart and bring them back together, you also change their state. So you split them apart. And then when you do their recombination, you first put them in a superposition of two different internal states, and then complete that transition and bring them back together. And then you get sensitivity to the interaction with the light. That allows you to measure the fine structure constant, which is one of these things that's tested to like 14 decimal places. And you can look for changes in fundamental interactions that way. You can also look at gravitation on really small scales. This is an experiment. These are both of these are from Holger Mueller's group at Berkeley. You could do this atom interferometer. You toss the atoms up in the air, separate them by some distance, then you turn on an optical lattice to hold them in place so they don't fall. They're supported by the lattice, and the two parts of the atomic wave packet are separated by whatever distance they were when you turned on the lattice. You can hold them there for a substantial time and then release them and complete your atom interferometer. They do this either with the two wave packets just below a tungsten test mass, or with them just above a tungsten test mass. The gravitational attraction will add phase to either the top or the bottom of those wave packets, and you can see that change in phase and look for the effect of gravity on sort of centimeter scales by, if we do this in those two locations with the mass there, is that different than doing this in those two locations without the mass there? And they can see, test the effect of gravity. General relativity continues to work. They haven't seen anything. They haven't seen anything squirrely with it yet. But this does tell you that that it works to phenomenally good precision. So that's a whole lot of things involving atoms to this point. The last of the quantum 2.0 things that I'll mention, pretty good on time. Last thing I'll mention is what happens when you really take into account the particle nature of light. So we can think about the state of light in terms of particle language and wave language. And then, a beam of light, you think about, well, it's got some intensity. I can map the intensity to some number of photons. I can also say it's got some phase associated with it. which then it becomes a property that's associated with the individual photons. I want to describe this state collectively. I can represent it as, say, a vector that has some length. The length of the vector is proportional to the number of photons, or it's really the square root of the number of photons. But it's related to the number of photons, and then it has a phase angle that is related to the passage of time. So I have this phasor representing my light wave. It starts out on the x-axis and then clocks around accumulating phase as time goes by. All right. This is a thing we can do. However, since these things are quantum, right? They are both particle and wave nature. This uncertainty relations come into play, right? There's this indeterminacy to have both the particle and the wave nature introduces this element of uncertainty, which in this case manifests as an uncertainty in the number of photons that you have present in your beam and an uncertainty in the phase of that beam. Right, so that phase angle, there's some uncertainty. Then how many atoms you have has some uncertainty, and the product of those two things has to be greater than some minimum value. Happens to be a half, and you can understand this in various different ways. What this looks like in these phasor diagrams is at the tip of the arrow representing my vector, representing my light field. Right, the position of that is sort of smeared out. Right, the tip of that vector is somewhere within this fuzzy shaded region that's represented there, but I can't say for certain where in that region it is. Right, and this puts limits on if you want to compare the phase of two lasers, say doing an interference experiment, compare the phase of two beams. Right, this uncertainty limits your ability to measure that. Right, limits your ability to do that measurement if you're dealing with beams with relatively few photons in them. You're going to have to run up against this uncertainty in phase that's imposed by the fact that you've got this quantum nature of these things. So that's Werner Heisenberg ruining everybody's day. But there's a loophole to this. Right, the loophole is, right, it's the product of these uncertainties that's subject to a constraint. All right, right, I have to have an uncertainty in the number and an uncertainty in the phase such that their product exceeds some minimum value, but that doesn't constrain either one of them, right? And if I do a type of experiment where I only care about one of those things, I could reduce the uncertainty in that thing at the cost of throwing away information about the other. Right? So what I could do is I could make, in the phasor picture, I could make a state where the area, right, the product of the number uncertainty and the phase uncertainty is the same, but I've made one of them bigger and the other one smaller. Right? I can reduce my number uncertainty by squashing that round uncertainty region down into an ellipse. So long as the ellipse gets bigger in the other direction. All right. So I can, and if I'm doing an experiment where I only care about the number of photons that I have, I'm willing to throw away information about the phase. That could be a trade-off that I'm willing to make. This is referred to as a squeezed state from the appearance of this phasor diagram. Right? It looks like if you take a round balloon and you squeeze it between your hands, it's going to spread out in the other direction somewhat in a way that keeps sort of the overall area constant, but reduces the size in one direction at the cost of increasing it in the other. How do we do this? There's sort of two ways of making squeezed states of light. One of them is, both of them use nonlinear materials. One of them is you just send your light through a medium that has an intensity-dependent index of refraction. This is referred to as a Kerr medium. What that does is that means that higher intensity states with more photons, accumulate phase faster, right? So if I were to think about this as, there's my phasor, it starts off on the x-axis, sometime later it's rotated up to some angle, right? But my actual phasor could be anywhere in that circle. And if I'm on the higher photon number side, right, it accumulates phase faster. That high vector rotates more through a larger angle. If I'm on the low number side of that uncertainty region, it rotates less, right? And then that naturally takes what starts out as this round uncertainty region, right, with equal uncertainties, equal-ish, for a given scaling of the axes, uncertainties in number and phase, turns it into an ellipse because the high, things on the high end of the number range accumulate more phase and sort of stretch out. The area of that thing stays the same. You can show that it's constrained to whatever area you start with. You have to end up with the same area. So this does exactly the thing you want. It makes a number squeezed state through this nonlinear acquisition of phase. The other thing you could do is think about this really in terms of the photons as particles and the numbers of the photons. And then what you use is a frequency doubling medium. So you use a nonlinear medium that's going to double the frequency of your initial beam. And what this does is upward fluctuations in the number of photons in a short window of time, those get converted into photons of twice the frequency. Right, so I can think about my beam of light as some number of photons. I chop it up into short time intervals. I say how many photons are in each of these bins, right? And so here's 3, then 1, then 1, then 1, then 2, then 0, then 2, then 0, then 3. Right, different numbers of photons in different bins. What this nonlinear medium will do is basically take 2 photons that arrive within a short enough time of one another, and take the energy of those 2 photons and convert it into 1 photon with twice the frequency. What that does to your beam is, places where here I've got 2 photons in a very short amount of time, right, 2 infrared photons in a short amount of time, that turns into, right, 1 blue photon, and the other photon that was in that bin is left by itself, right? Here's another place where there's 2. Right, it turns into 1. Here's another place where there's 3, turns into 1 and 1, right? What this does is this sort of chops off the high intensity end, right? The number of photons per time bin here will be subject to some statistics. You work through the math. It's Poissonian, is a Poissonian distribution. So there's some average number with an uncertainty equal to the square root of the average. Right, that initial Poissonian state, things on the high end get chopped off and turn into photons in the other distribution. And you end up with sub-Poissonian statistics in both cases. All right, that's another example of a squeezed state. Right, you've taken the uncertainty in the number of photons in your beam in any particular time interval and made it smaller by taking some of those photons out and shifting them to a completely different frequency range. Right. So what this looks like, these phasor kinds of pictures, you can see here's like a squeezed state. A coherent state that's a state, the minimum uncertainty state with equal uncertainties in number and phase at the very top, right? Then a squeezed state. If you look at what this means for, say, something we were trying to measure the electric field, as that thing clocks around, you have places where the uncertainty in the electric field is very large and places where the uncertainty in the electric field gets very small. So if you're doing an experiment, right, where you care about, I do something that makes my uncertainty ellipse look like that one in B, right, at some instance in time, my uncertainty in the electric field gets very, very small. And if what I care about is that, right, then I could do a much better measurement of that thing than I could with a classical state, with the coherent state. This shows up, the classic way of measuring this is to look at the shot noise, right? You just take one of these beams, shine it on a detector, look at the noise of the signal that comes out as a function of time, and what you see is normally that's, you know, this curve here, this black horizontal noisy line. If you, this is the quantum, or this is the minimum you could achieve. If you put it in one of these squeeze states, as it evolves over time, sometimes the uncertainty is considerably higher, sometimes the uncertainty is considerably lower, and in a way that is, you know, changes in time as this phasor clocks around. The other really cool thing with this is you can squeeze the vacuum. All right, so one of the fascinating things about this photon picture of light is that empty space is not completely empty, right? Say, you know, I have some region of space that has 0 photons in it. It actually has 0 photons in it on average, right? But there's some fluctuation in that 0 photons that takes the form of a state with some uncertainty in the number of photons you have and some uncertainty in the phase of the photons that you have or don't have. And you can squeeze that too. And why would you squeeze vacuum? Well, if you think about an interference experiment, what you're doing is you're interfering, you know, the inputs of your interferometer, you have like a light beam coming in this way. The other arm of the interferometer, you have whatever the vacuum is coming in. So you're really interfering the light that comes in with its, you know, and plus the vacuum coming in the other port of the interferometer. So if you squeeze the vacuum, you can actually enhance the sensitivity of your interferometer by reducing the uncertainty of the 0 photons that you're sending in through the other arm. And so this thing here shows the effect of squeezing the vacuum. Right, the vacuum starts out as a round area centered at the origin, 0 number, right, irrelevant phase. If you reduce the uncertainty in one of those quadratures, you get, as you compare it to anything else, you get this fluctuating. This oscillating, you know, narrower and wider regions of sensitivity. This is the one place where I will slightly step on one of the speakers later in the workshop, which is this has actually been put into operation at LIGO, and I think is a thing that we'll hear about on, I believe it's Friday. Is that LIGO has made use of this idea of squeezing to enhance the sensitivity of their interferometer. They have to do, because they're looking at all these wide ranges of frequencies at which the mirrors can be moving farther apart and closer together. They have to take different approaches in different areas. They do some complicated tailoring of the way that they squeeze the beam. So they're squeezing the amplitude in one region of frequency and the phase at other regions. But the upshot of this is get this right. The black line here is the noise signal is their sensitivity to changes in the length of the arms of the interferometer at various different frequencies without doing any squeeze state stuff. And the purple line is the sensitivity with the squeeze states. So you see it's substantially better over a wide range of frequencies, enhancing the sensitivity of LIGO, and that gets you a reduction in noise floor. So, you know, again, Michelson and his interferometer coming around again, and this time finding a loophole to get around Heisenberg's limits on what you can measure with these indeterminate quantum states by taking advantage of this squeezing phenomenon. So that's a list of things that I would class as solidly quantum 2.0, in that they're using those, I said 1.0 is sort of lasers and transistors, right, that are things that depend on quantum for their operation, but in practice are used essentially classically. But those are tools that you can then kind of bootstrap to make things that take advantage of quantum effects in a richer way. And so things like doing experiments with single photons, exploiting quantum entanglement, using this incredibly sensitive state control to make systems that are more sensitive to external perturbations, being able to read them out through Ramsey interferometry. These quantum degenerate systems allow you to do some really interesting things. Atom interferometry using the wave nature of the atoms to do interference experiments to pick up these tiny changes in phase, and then squeezed light as a way of taking this Heisenberg limit that seems like a complete disaster for any kind of measurement thing, and actually putting it to use by saying, well, if I only care about one of these two quantities, I can reduce my uncertainty in that and throw away information about the other. So huge range of tools and techniques. I've kind of given like one or two examples of each of these things. There's dozens of examples of people using all of these ideas for ultra precise measurements. And the end result of this is, some of the tightest limits we have on exotic physics theories, and correspondingly some of the best chances we have to detect new physics in the future. Because if we're going to look for new discoveries, we need to be looking in these days the 16th or 19th decimal place to find anything new. So that's my 30,000-foot overview of quantum sensing. I think the other speakers here will be talking about things that are kind of inhabiting this space, ways of preparing atomic states in a way that's particularly sensitive to magnetic fields, or particularly sensitive to particular kinds of perturbations, and using that sensitivity as a way to detect things for practical ends, not just this exotic particle physics stuff. So thank you very much for listening. I hope that's helpful. And happy to answer questions.
All right. Any questions?